You know that feeling when you try to get an AI to analyze a huge document, like a massive code base or a really long legal contract, and it just chugs, or maybe it just flat out fails? Well, the reason isn't always about raw compute power. There's a hidden memory bottleneck that's costing companies billions. Today, we're pulling back the curtain on that exact culprit and two absolutely brilliant hacks that researchers have designed to conquer it.
So let's meet the main character of our story today, the KV cache. The easiest way to think about it is as the AI's short-term memory. You see, when a model is generating text, it needs to remember what it just said. The characters, the plot, all of it. The KV cache stores all that context so the model doesn't have to reread everything from the beginning for every single new word. It's crucial for making things run efficiently. But, as you're about to see, this memory has a bit of a dark side.
And here is that dark side. Get this, researchers found that for a single document with a 512,000 token context, which is long, yeah, but becoming more common, the KV cache can swell to over 93 gigabytes. Now, to put that into perspective for you, a top-of-the-line NVIDIA A100 GPU, the kind of hardware these models run on, has 80 gigabytes of memory. The AI's short-term memory is literally bigger than the super expensive specialized hardware it's running on. That is a massive problem. Okay, so this memory crisis isn't just a small issue. It's a major bottleneck for the entire AI industry, and it's holding back what these models can really do. But whenever a problem gets this big, it inspires some truly brilliant solutions. In this case, we're looking at not just one, but two fundamentally different and frankly, equally clever approaches. It's a tale of two strategies, each tackling the same billion-dollar problem from a totally different angle.
The first strategy really begins with a basic hardware trade-off that we're all kind of familiar with. On one hand, you've got your GPU memory. It's incredibly fast, but it's also incredibly expensive, and you just don't get a lot of it. On the other hand, you have your regular system RAM, the CPU memory, which is way slower, but it's also cheap and you can have tons of it. So the obvious idea is, why not just store that giant KV cache on the cheap CPU memory? Well, the problem is that the connection between them, the PCIe bus, is like a slow, narrow bridge. And that's the whole challenge.
And this brings us to our first solution, a system called CLO. For today, let's call it the mover. CLO's whole philosophy isn't to change the cache itself, but instead to become a master logistician, to intelligently and super efficiently move the right pieces of the cache from that slow, big CPU memory over to the fast GPU memory at the exact moment they're needed.
And being smart about this move is just crucial. This chart really drives the point home. The first bar, that's the ideal scenario. That's the time a system should spend on useful work. But look at that second bar, representing older systems. All that extra height? That's pure waste. It's overhead from managing the cache, waiting for data to transfer, and the CPU and GPU just not being in sync. It more than doubles the processing time. And that is exactly the inefficiency that CLO is designed to get rid of.
So CLO attacks this wasted time with four really key innovations. First, instead of some complex management system, it just uses a smart approximation to predict what data the GPU will probably need next. It also keeps the absolute most critical data permanently on the GPU, no moving required. Then it uses something called a zero-copy transfer. You can think of it like a direct, high-speed tunnel from the CPU memory straight to the GPU, bypassing any bottlenecks. And finally, it flips the whole script and lets the GPU tell the CPU when it's ready, which gets rid of all that idle time. It's all about making that data transfer as lean and mean as possible. And the results? Well, they're pretty impressive. The creators of CLO found that their system improves the overall throughput by up to 66%. Just by mastering the logistics of data movement and cutting out those CPU bottlenecks, they made the entire process dramatically faster.
Now, that is a fantastic solution, but it does spark a different question, right? Moving massive amounts of data efficiently is one thing, but what if you didn't have to move it at all? What if you could just make the data itself smaller, so small that it fits on the GPU in the first place? And that question leads us directly to our second solution, a system called KV Quant. Let's call this one the shrinker. Instead of being a logistics expert like CLO, KV Quant is a master of compression. Its entire goal is to shrink the KV cache itself, but to do it without losing the vital information the model needs to actually work properly.
The core technique it uses is called quantization. Now, that's a fancy word, but the idea behind it is actually pretty simple. You're just reducing the precision of numbers to save space. Think of it like this. An old analog photograph has an almost infinite amount of color detail, right? Well, a digital image saves space by representing that photo with a limited palette, like 16 million colors. Quantization does the exact same thing, but for the numbers in the KV cache, reducing the number of bits it takes to store each value.
In this slide, this reveals KV-Quant's key insight. It's the aha moment. On the left, you see the raw KV cache data. Notice it has these clear, structured patterns. But then models apply a process called ROPE, that's rotary positional encoding, which basically gives the data a sense of word order. The result is the image on the right. See how it's more chaotic and much harder to compress? The absolute genius of KV-Quant was realizing they should shrink the data before ROPE, back when it's still clean and structured.
So building on that core insight, KV-Quant uses a few other clever tricks. It quantizes before ROPE, as we saw. It also applies different compression rules to different parts of the data, because hey, not all information is equally important. And it uses this brilliant dense and sparse method. It basically finds the most important 1% of values, the outliers, and keeps them in perfect, full detail. And then, it aggressively compresses the other 99%. It's like data triage.
And the payoff for all this cleverness? Oh, it's huge. Just look at these numbers. For a llama model dealing with a 1 million token context, the original KV cache would be an absolutely impossible 512 gigabytes. But by using KV-Quant's shrinking technique, it gets crushed down to just 64 gigabytes. That is an 8 times reduction in size. It goes from totally impossible to actually manageable.
The result of this is just staggering. This level of compression makes things possible that were pure science fiction just a year or so ago. With KV-Quant, researchers were able to demonstrate a 10 million token context length running on a standard 8 GPU server. To give you an idea of how big that is, it's like feeding an AI the entire Lord of the Rings series, including all the appendices 7 times over in a single prompt.
So, where does all of this leave us? We've just walked through 2 incredibly powerful, yet completely different solutions to AI's giant memory problem. So what does this all mean for the future of AI?
Well, we're left with 2 brilliant paths forward. On one hand, you have CLO, the mover. It treats this as a logistics problem, and it perfects the art of moving data just in time to make offloading to cheap memory super efficient. And on the other hand, you have KV-Quant, the shrinker, which treats it as a data problem, compressing the cache itself to unlock context windows we could only dream about before.
Both of these approaches are effectively breaking the memory barrier. They're turning context length from a hard physical limit into a solvable software problem. And that leaves us with a really fascinating final thought. Now that we have a path to a nearly infinite memory, what new capabilities will these models unlock? And what's going to be the next great challenge that stands in AI's way?